Okay, so now we want to find a basis for the null space of this fairly large matrix here. So just to be sure you can read the entries. First row is 1, 0, negative 5, 1, 4. Second row, negative 2, 1, 6, negative 2, negative 2. And then 0, 2, negative 8, 1, 9. Okay, so remember, null space is find the solution set to the equation ax equals 0. Right, that's the null space. The solution, the collection of all solutions to this vector x, where we have ax equals 0. So when you find null space, the idea is you augment this with the 0 vector here, since we want to find when this is equal to the 0 vector, and then row reduce this thing. So I would do 2 times row 1, good old row reduction, plus row 2. So we'll get this 2 times this, so negative 10, so negative 4, 2 plus negative 2, and this will be 8, right, plus negative 2, so 6. Okay, I'll leave this one. Okay. I'm not going to carry around the 0 column because any row operations, if I do 2 row 1 plus row 2, that's going to be 0 plus 0. When you have a column of zeros, it's just going to stay a column of zeros every step of the way. So I'm not going to carry that 0 column around every step just to save a little space here. So I would now do negative 2 row 2, add that to row 3. Let's see. So that'll give us 0 plus 0, negative 2 plus 2. This will be positive 8 plus 8, 0 plus 1, and negative 12 plus 9, so negative 3. Okay, so right here we know that, let's see, x3 and x5 are going to be the free variables. Okay, but when there are infinitely many solutions, I like to get it all the way to the reduced row echelon form. So when we're almost there, right? We just need to get a 0 in this position here. So I think it's worth it to do that one extra step rather than deal with a lot of back substitution. Whoopsie. Okay. Sorry. Okay. So I'll do negative 1 times row 3. I know I'm in the way. Plus row 1. Come back over here. So row 3, row 2, and the new row 1. So 0 plus 1, 0 plus 0, 0 plus negative 5. Negative 1 plus 1, and positive 3 plus 4. Okay, so now we've got this thing in the reduced echelon form, or RREF form. So now suppose I'm going to bring in that column of zeros that would have been there all along. So that means that our solution set, let's see, looks like this. We've got x1 minus 5x3 plus 7x4 equals 0. So, well here, okay, and then x2 minus 4x3 plus 6x4, and let's see, 1, 2, 3, 4, x4 minus 3x5. Whoopsie. Yeah, these should be here, x1, x2, x3, x4, x5. So these should be 5s. Sorry about that. There we go. So our solution set looks like this. If I solve for x1, x1 is equal to 5x3 minus 7x5. Okay. x2 is equal to 4x3 minus 6x5. And then x4 is equal to 3x5. Okay. Then I have to get rid of this. So that means, kind of want to keep our reduced form here. I'm going to use that later. So our free variables are x3 and x5. Those are our parameters. So any solution to this ax equals 0 equation, x will have to be, and let's go ahead and set up the parameters. So the free variables are x3 and x5. So let's let x3 equal s and x5 equal t. So that means that x1 is equal to 5 times x3, which I'm calling s, minus 7 times x5. x2 is equal to 4 times x3 minus 6 times x5. x3 is s. x4 is equal to 3 x5, and x5 is t. Let me expand this a little bit. And so just to be clear, so this is x equals, this is your x1, x2, x3, x4, x5, when we substitute in what we've just set up there. And so that means that it's s times this vector plus t times this vector. Negative 6, 0, 3, 1. So any solution, x here, so any vector x in the null space, is going to be a linear combination of these two vectors. So these two vectors span the null space of that matrix. So they span, remember that's one of the criteria. The other one is that they're linearly independent. These guys are linearly independent. If we combine these, so say we put them back together. So say we take this expression here, set it equal to the 0 vector. So then you would combine them, you get this expression here equal to the 0 vector. Well, then that's going to imply that s must equal 0 and t must equal 0. So that's going to imply that this equation here has only the trivial solution. S has to be 0 and t has to be 0, because this entry has to be 0 and this entry has to be 0. So only the trivial solution. That means that these vectors are linearly independent. So they're linearly independent and they span the null space. That means that this right here is your, I lost the lid. I'll let my marker to drop. But this right here is the basis. So a basis for the null space of A is the collection containing these two vectors. And just in general, this is how you find a basis for a null space. Is you just, when you find the null space, write it in parametric form, then these vectors from your parametric form will constitute a basis. Because they're always going to be linearly independent and they will always span the vector space.